So I just flew in last night, red eye from San Diego, the pleasant weather of San Diego, uh, because of the all week joint mathematics meeting. So if I'm stuttering or I'm not making any sense, please excuse me. Um, so I'm gonna talk about the homological theory of functions. So first of all, what is homology? What is this? What is this thing? What is this weird word I'm saying? So in short, it's coming from algebraic topology, which is an area of pure math. And simply stated, it's a study of holes in topological spaces. Um, and for example, a circle has a dimension 1 hole, right, in the center. A sphere, a hollow sphere, has a dimension 2 hole, a hollow sphere, right? And what is the dimension 0 hole? So you can think of it as the equator of the circle, which is 2 points. So that's the dimension 0 hole. In general, we want to study holes up to continuous deformation. So in particular, a square, a hollow square, has the same hole up to continuous deformation as a circle, and a hollow cube has the same hole, a dimension 2 hole, as a hollow sphere. Okay, so that's all I'm going to say about homology. I think I'm going to keep everything intuitive by just saying holes instead of homology. Okay, so what about the computer science side? In computer science, we like to study function classes, right? So they can come from learning theory or computational complexity. And in this framework, we want to associate function classes with topological spaces and use tools from algebraic topology and centuries of these insights to give us something about computer science. In particular, we're going to focus on the structure of holes, the homology. And the tools we're going to use are commutative algebra, this thing called Sanity-Reasoner theory, and cellular resolution. So I'm not going to say any more about these things. Just if you do know what those are, that's for you. Okay, so let me talk a little bit about the spaces we're going to build. So these are particular combinatorial topological spaces. They're called simplicial complexes. And in short, you can think of them as some kind of gluing of simplices together in a proper way. So I'll give you some short examples. So this is okay. We're gluing edges to edges between triangles, and this is not okay. We're gluing a point, a vertex to an edge. Okay, and that's all I'm going to say about this, and we're going to keep it intuitive. Just think of it as gluing of triangles, tetrahedrons, and so on. Okay, so now let's get to the connection between algebraic topology and computer science. And this is what I'm going to propose. So first of all, notation, just for simplicity's sake. Bracket n is just a set of n elements, and bracket n to m is just a set of functions from n to m. Okay. So here's the key construction. For a class C, whose functions have common domain n and common codomain 2, we associate this simplicial complex S sub C, which is given by the vertex set is n times 2, and the facet, which is the maximal simplices in the simplicial complex, there's one for every function in the class. And the vertices are corresponding to the graph of F. So this is probably very confusing right now, so let me give you some examples. Okay, so let's look at the set of all functions from 2 to 2, which is just bit functions. There are 4 of those. So I listed the table of their graphs here. And the 4 functions, I just wrote it as true, false, identity, and negation. Okay, so let's look at the definitions again. So there's a vertex set, n times 2, that correspond to a pair, one element of the domain and one element of the codomain. And so I labeled the points here, therefore. And there's one facet for each function in the class. There are 4 of them. So for example, let's see. So let's look at this. The true function, it sends 0 to 1 and 1 to 1. So what we're going to do is draw in a 2 simplex, which is just an edge that connects this vertex, that sends 0 to 1, and this vertex which sends 1 to 1. Okay, and the other functions you can construct facets similarly. So in the end, what we're gonna get is this shape, and in particular, this in the center here, there's nothing there. It's a hole. So you can see that the homology structure, the structure of holes is non-trivial. Okay, so what happens in general is that if you generalize this construction, replacing the domain by an arbitrary set of n elements, the complex you're going to get is in general an orthoplex, which explicitly is the boundary of this convex hull of plus and minus coordinate vectors. So in 3 dimensions, it's an octahedron. It looks like this. And if you look at the structure of holes, it has a single hole at dimension n-1. Okay, and if you look at general classes, not necessarily complete classes, they're going to be subcomplexes of this orthoplex. They're going to be formed by choosing a subset of the facets. Okay, I'm going to give you one more example, a bit more non-trivial example. So let's consider the class of F2 linear functionals. So for this particular example, we're going to consider dimension 2. So let's take the input space to be non-zero column vectors, F2, 2, and the function class to be the row vectors in F2. So here's the table of graphs again. Here, these are column vectors are inputs, and row vectors are the functions. And these values are obtained by just matrix multiplication. Okay, so I'm not gonna actually show you how to draw this from step by step. I'm just gonna show you the final result. So I'll remark to you a couple of things. There are 6 vertices, each correspond to a pair input times output. And the green guys, the green row vectors correspond, they label the facets, these triangles, in the complex. Okay, so in particular, there are 4 facets. In case you can't really see it, in 3D, here's the spinning version of this. So you can see that there are a bunch of holes in there. So they're, naively speaking, there are like 4 holes, but actually only 3 are linear independent in a specific sense. So again, you can see that the homological structure, the structure of holes, is highly non-trivial. Okay, so that's the construction. So what does this have to do with computer science? So I'm gonna claim this statement: the amount of data needed to learn an unknown function in a class C is controlled by the homology of C. So what does that even mean? So let me refine this a little bit. The amount of data needed to learn an unknown function in a class C is controlled by the highest dimension of any hole in C. So this is almost a statement I want to show you, but not quite. There's some modification there to make it actually correct. And this is the right statement, but I'm not going to explain to you what this thing means. For all purposes, you can just think of this as a correct statement, because in most cases, these two are equal. So just forget the links, and I'm going to define this quantity here, this thing, as the homological dimension of C minus 1. So this is off by 1, but you can forget about the 1. Okay, so what do I mean by this? Here's the precise statement. If you precisely define homological dimension, so the key theorem is that, at least in this section, is that the VC dimension of C is upper bounded by the homological dimension of C. So in case you don't remember VC dimension, let me remind you what it is. So this is a classic learning theory quantity. It is the size of the largest subset of the input space, such that C shatters U, which means that C, when you restrict C to the subset U, you get all of the Boolean functions on U back. Okay, so in some sense, you can cut out every subset of U. So it shatters U. And by classic theorems in learning theory, VC dimension is about the number of ID samples you need to learn a real function, a known function in a class, given data. And this is a high probability statement that I'm going to kind of avoid the probability statements. Okay. So in fact, yeah, let's look at some examples to convince you that this is actually a real phenomenon. So here we have the example of the class of all functions from 2 to 2. And so this is that's the complex. The dimension of the highest dimension of any whole is just 1 because this is a homeomorphic to a circle. So it has a dimension 1 whole. So 1 plus 1 equals 2, which is the VC dimension. So in this case, they're actually equal. If you generalize this to arbitrary n, the domain, you make it larger, you're going to observe the same thing. So in general, the complete class of on the domain of n elements will determine an orthoplex, which has a whole of dimension n minus 1, plus 1 of that, that's n, which is the VC dimension. Okay, so something a little bit less trivial. If you look at, so this is a reminder, this is the complex we looked at just now for linear functionals over F2. Okay, so this complex, the highest dimension of any whole in here is just 1. If you can't see it, maybe we can talk about this afterwards. But so it's 1, and 1 plus 1 equals 2. So this is and 2 is the VC dimension of the class of parity functions over F22. So again, in this case, they're actually equal. And I can actually tell you more cases where they're actually equal. So for example, polynomial thresholds, which I'll actually talk about a bit later, VC dimension is equal to homological dimension, monotone conjunctions, and there's something called Macaulay classes, which kind of is an idea from commutative algebra. Okay, so there's a lot of equality cases. However, in general, they're not equal. There are examples where actually the gap can be exponentially large. So one of the open problems is to characterize when can we expect equality and when can we expect something like O to 1 gap or log n gap. Okay, so if you have the machineries, for example, the thing, Stanley reasoner theory I mentioned, to prove this inequality is not actually too difficult. But I'm not going to assume any of that. So I'm going to just give you a taste of why homology would ever play a role in this context. Why would homology even matter? So I'm going to claim the following, that C shatters U. Remember, this is when you restrict C to U, you obtain all Boolean functions on U. I claim that this C shatters U if and only if, whatever this means, the U equator of the complex SC associated to C is isomorphic to a sphere of dimension U minus 1. So S, in the second instance of S means sphere. So I'm not going to explain precisely what this means, but I'll just give you a picture. Okay, so here's the complex we had for F2 linear functionals. And suppose I want to look at whether C shatters U, where U is 1, 0, and 1, 1. So the points I have, first coordinate 1, 0, and 1, 1 are these 4 points. So the U equator intuitively is this green square here. And you see that if you think about it for a moment, you see that this linear functionals, they shatter U, the parity functions, they shatter the set. And at the same time, you have that the subcomplex is a square, so it's homeomorphic to a circle. And so this is kind of pictorially, that's what I want to say about this, but I'll go no further. Okay, so that's all I'm going to say about homology and learning theory. In the rest of the time, I'm going to pack in some things I want to say about homology and complexity. So let's give a new look at an old result. So the definition, I want to make a definition first. A polynomial threshold function has the form that sends x, which is a bit vector, through a polynomial first, and then you threshold that so that if it's polynomial returns a positive number, you put 1, and a non-negative, non-positive number, it returns 0. Okay, so this is a classic theorem of Minsky and Pepper, which says that the parity function pi, which I'm going to write here, denote here as pi, which just takes the input bits, take the sum of them mod 2. It is not a polynomial threshold function of degree less than k. So non-maximal degree. Actually, I should have used D here instead of K. Okay, so here it is again. I'm just going to shorthand the class of polynomial thresholds, degree-bounded polynomial thresholds, as this notation here. And so this is the restated version of Minsky-Pepper. Okay, so what can we say homologically about this? So what happens homologically is that if you look at the class of polynomial thresholds with degree bounded by k, it has a single hole in some high dimension. That's essentially equal to its VC dimension. It has a single hole there. When you add parity to the class, so this is the parity, it actually covers up this hole. And you can detect this change in the homology. So as a result, because your space changed before and after you added the function, so the function must not have been in the class to begin with. So that's a homological way to prove Minsky-Pepper. So Minsky-Pepper is not terribly difficult. It's actually pretty easy to show without any fancy stuff. But we can generalize this a little bit in two directions. So I'm gonna define a weak representation, which is the following. So a Boolean function f, we're gonna say the image, the domain is 1 and minus 1, is weakly represented by a polynomial p if f is equal to the sign of p whenever x is non-zero. Sorry, p of x is non-zero. Okay, so it's kind of this is related to the Minsky-Pepper result, in that Minsky-Pepper also deals with representation of a function as a sign of a polynomial. But the other sense, the Minsky-Pepper sense, is a strong sense in which you send whenever p of x is 0, you take f of x to be negative 1. In this case, we don't care when p of x is 0. Okay, so the following is true, which is quite remarkable. F is not weakly representable by a polynomial of degree k if and only if, when you add the function f to the class of polynomial thresholds and look at its complex, it has no holes. So remember, when f is not, when you just look at the complex of polynomial thresholds, it has a single hole at the dimension equal to its VC dimension. When you add f, if it has no holes, then f is not weakly representable by a polynomial degree k. So here's a pictorial representation. So suppose you add f and it covers up that hole, and that means that f is not weakly representable by a polynomial of degree k. On the other hand, suppose he kind of covers up a bit of it, but not entirely, so that there's still a hole in the union, then f is still weakly representable by polynomials of degree k. Okay, so there's one final thing I want to say, and it requires me to define another concept called polynomial threshold degree, which is the smallest k such that f is in polynomial threshold of degree less than or equal to k. So there's a classic theorem by Espinez, Bagel, First, Rudich, that characterizes the polynomial degrees of all symmetric functions. And so we can actually prove this as well from homology by looking at perturbation of low-dimensional holes. So in the previous example I gave, we looked at how the highest dimension hole of the complex is covered up when you add in a function. So in this case, what we're going to do is look at subcomplexes of the simplicial complex and see how low-dimensional holes of those subcomplexes change when you add functions to the class. And in fact, the principle that we're actually going to use, we can extract the general principle from the proof here, which is very, very intriguing. So let me dial back a little bit. In general, suppose you're just fitting a polynomial, like so a continuous, we're talking about continuous things now, fitting a degree k polynomial to data. This is a convex problem if the loss is L2. So local minimum implies global minimum. Okay, but there's something similar for polynomial threshold, interestingly. So let's define G to be local minimum in class C for approximating another function f. If, first of all, G is a member of C, and for each function h in C that differs from G on exactly one input u, so kind of a point in the neighborhood, a function in the neighborhood of G, we have that on that single point, G correctly gives the value of f, but h does not. So G is a local optimal for approximating f. Okay, so the following is true, and we can show this using homology. So the convexity of this polynomial threshold class. So if C is this polynomial, the rebounded polynomial threshold class, and we fix a function f, we're thinking about whether f belongs to C or not. So whether f can be strongly represented by a polynomial. So if there exists a local minimum G in C for approximating f, and G is not equal to f, then f is not in C. So in some sense, G, like any local minimum of, for approximating f has to be a global optimum. And if this global optimum is not f, then f is not in the class. Okay, and so that's all I'm going to say about homology and computer science. And the last thing, I don't know if this is ethical to do this, but I'm just going to advertise a program for Microsoft. So there's just, we're running a program on the AI residency. And it's a one-year program at Microsoft. We're trying to create the next generation of AI researchers. And we want both theoretical and applied computer scientists toward the next AlphaGo moment. So if you're interested, we can talk afterwards. Thank you. Yeah.
I'm wondering if there is a way to handle approximate representations in your framework. Let's say I want to understand if I can epsilon through some other approximate a function by polynomial threshold.
Yeah, so there is a way, but we don't, like the technology there is not up to par, like not the same standard as this. So so we can talk about this afterwards, but like essentially the motivation from the beginning was to kind of quantify all of this approximation. But at some point, I realized that if you just ignore the numbers, you actually get something really nice. So I pushed forward in this direction. But there is something that we can talk about afterwards that goes that way. Yes?
The definition of dimension give us in abundance over the standard definitions of VC dimension?
I'm sorry, could you repeat that?
So does your definition give us some more tools like that go beyond the standard like VC dimension to attack some different like problems in terms of like characterizing complexity?
Yeah, I mean, we believe so. I think so to even extend your question, even the insights around this homological dimension, which is a single number. So if you actually look into the homology, like so I hit a lot of details about how you construct all these things. But there are a lot of topological structures that you actually obtain when you do these analyses. And they reveal really interesting insights on the structure of the class themselves. So just to give you like a taste, which wouldn't make any sense. So if you look at the class of monotone conjunctions, it corresponds in some sense to a cube. If you look at the class of conjunctions, it corresponds to what's called a pile of cubes. So like 2 times 2 times 2 of cubes, and then a pyramid on top of that. And polynomial thresholds correspond in a dual sense to spheres. So like a lot of these are actually like highly non-trivial statements about the structure of the class. And we're pushing forward on deriving new complexity or learning theory results from that angle.